Let me remind you that we had introductory lectures regarding where and how elements originated, after which the predictions of Gaumov's classic theory about the limits of the stability of atomic nuclei were shown, which was then further developed by other great scientists, including Niels Bohr. It was then assumed that the droplet model was valid, and therefore assumed that no nuclei of elements heavier than atomic number 100 could exist. The fact that heavier nuclei, such as elements 102 and 103, were obtained at FLNR, did not change the matter, because a sharp change in the lifetimes supported the prediction that the limit was not far off. However, further experiments showed that a drop analogy existed for the nucleus as a microscopic body. At the time, it was not always possible to consider the nucleus as a macroscopic body. And the biggest discrepancies or inconsistencies in terms of macro-micro were observed during the discovery of spontaneously fissioning isomers. It is possible to have a micronucleus, but as was explained later, a macronucleus is completely impossible. After describing all deviations from the classic theory in the form of corrections of the internal structure of the nucleus, an unexpected prediction was made. Where, according to the droplet model, there should not be any nuclei with a lifetime of less than 10 to the power of minus 19 seconds, it turned out that new shells, new magic numbers, new structures, and a fission barrier appeared. Nuclei can actually live for a very long time. This is a very ephemeral structure. The structure is ephemeral depending on the point of view. But this barrier is created with the structural correction, and there is enough energy to create a barrier of several mega-electron volt, enabling the nucleus to live for a long time. Then various reactions took place which were used to synthesize heavy and very heavy elements, starting from the first transuranic elements when uranium was irradiated in a nuclear reactor. That is, these were neutron capture reactions. When underground explosions took place, neutrons were present. There were light elements, light ions, which could not reach this desired island. The very heavy ions, which were used in the reaction where the target was lead, were unacceptable because this ship was passing by the island because there was a lack of neutrons. In a fusion reaction, utilizing lead and some very heavy ions, such as zinc or germanium, the required amount of neutrons are not produced in order to get close to this island. Then it was about the fact that there are no other options. You just need to select both a target and a bombarding ion, each with a large excess of neutrons. An option was found in which, instead of stable lead, artificial elements are obtained in a powerful reactor, along with calcium-48, a unique, stable particle that is contained as a heavy isotope of calcium in very small quantities. This is a very expensive particle. It needs to be accelerated to about 1/10 the speed of light for a reaction to occur. In fact, this increases the complexity of the experiment. Here is the entire production history from the 1940s, depicted from the moment the first transuranic element was obtained. 8 elements were obtained with neutrons, and 6 elements were obtained with light ions. Another 6 were obtained in cold fusion reactions over 38 years. And this is the reaction that we have been working on from 1999 to the present day. Shown here in pink, which reaches the desired region of this island of stability of super heavy elements. This reaction has the advantage that the combination of calcium and the heavy nucleus is more asymmetric than these more symmetric ones when lead is the target. In this sense, the Coulomb repulsion directly at the entrance is much less than in a cold confluence. So the sharp drop which was here will not be as steep there. The Coulomb forces are shown here, and we can see how they increase with the growth of the atomic number of the compound nucleus. This is for cold fusion, and this is for the calcium and actinide. There is a big difference between them. It gains energy here. But with cold fusion, the nucleus turns out to be cold at only 12 to 15 megaelectron-volt. And with hot fusion, it is about 3 times hotter, and one must understand how long it will survive for. And what we see here is a sharp drop in the cross-section due to the fact that the nuclei do not survive as we move towards heavier and heavier elements. In fact, they do not survive because the fission barrier drops as one moves further and further from fermium. The fissionability of the nucleus increases, and as the nucleus cools by evaporation of neutrons, the contention from fission steadily increases. It was always believed that this option, although difficult, is not very reliable, because if one continues on this path, it will decline. If I remember correctly, I previously convinced you that it will decline if the barrier declines. But if the theoretical hypothesis that the barrier will grow is correct, then we should reach an island of stability, and then the cross-section should also increase. There was a hope that there would be an upward surge, and that this upward surge would lead to the synthesis of super heavy elements. Laboratories all around the world then began to irradiate curium with calcium, and we did the same in Dubna. This continued until the very last experiment was conducted in 1985 in a large collaboration between Europe and America. 22 experiments of various types were carried out on separators, with chemicals and with gas jets. This did not result in the synthesis of super heavy elements. However, the upper limits were obtained. Following these results, we did not share the scientific pessimism that super heavy elements cannot be synthesized. Rather, we concluded that it is necessary to significantly increase the sensitivity of the experiment.